All right, so we're going to be in your book today, page 117. We're going to look at these different situations or different possibilities with this country that's being described. Gentlemen, I need you to get your books out for me. So the population of the country that's being described, right now it's 2 million people. And it is increasing at a rate of 4% per year. The country's annual food supply right now is adequate for 4 million people. So do they have a shortage or a surplus right now?
Shortage.
They have a surplus because they have how many people? They have 2 million people and they have enough food for 4 million. It's increasing at a constant rate, adequate for an additional 500,000 people a year. If I'm thinking about the population, 2 million people right now, it's increasing at a rate of 4% each year. What kind of function are they describing? An exponential function. Whenever we see things increasing at a rate that is a percent, it is exponential. Mm-hmm. Yes.
It's without wouldn't that be a linear?
Mm-hmm. And that leads right into my next question. It's almost like I planted you here with that one. The food supply, is that increasing at a percentage? No.
It's a linear.
This one is a linear function. It's increasing to feed an additional 500,000 people. So this is linear. We saw yesterday when we were talking about which raise option is right for you, that if you initially chose the $3,000 raise, eventually the 5%ers were going to pass you, right?
Yeah.
That exponential function, while it started off lower, it did eventually cross and then pass the linear function of $3,000 each year. So this country is going to experience some food insecurity, some food shortages. They want to try to get ahead of this problem. And so they're trying to figure out how much time do we have to plan before these food shortages actually start impacting our population. I want to figure out in approximately what year this country is going to first experience shortages of food. So I want to begin by writing an equation for the population, which we said was exponential, right? And we're going to write an equation for the food supply. And then I'm going to give you guys some time, similar to what we did yesterday, where you can substitute in some values, and we're going to try to narrow down when this is going to happen, when they will no longer have enough food for all the people. Exponential functions. Yesterday, towards the end of class, we said that we write exponential functions as y equals a times b to the power of, we usually have t here for time. I'm going to go ahead and use t for time on this one also. What did this represent? That's the initial value. So what is the country's population initially? 2 million. Are you guys okay if we just use 2 and we know that it means million?
Yeah.
Okay, instead of writing out 2 with 6 zeros behind it. All right, so I'm going to have y equals 2 times, and then this right here,
4 million, isn't that the rate?
this is where we need to put what it's growing by, or sometimes we'll be looking at decay situations, but this is a growth situation. Each year it grows by how much? 4%, and that gets added on to the people that are already there, right? Do you remember how we represented that yesterday?
What we did on the table?
Yeah, when we wrote the equation at the very end of class. Because the population isn't just going to be 4%, it's going to be 4%
Time?
added on to the whole thing.
I thought you had to multiply and add.
What'd you say, Niles? 1.04. So the population goes from right now, 100% of everybody, and then we're going to add on an additional 4%. So we'd say the population next year is 104% of what we have now. So 1.04 to the power of t.
So is that for all?
Anytime they give us percents and it's growing, we take 100% and we will add on the percent that they give us in decimal form. If it's decaying, if it's getting smaller, we would do 100% minus the amount that it's decaying by.
So wait, if it's minusing, what would it look like?
If it's minusing, then I would have a number that's smaller than 1 in here. It would be like 0.92.
Okay.
That would be if it's going down. But this population's getting bigger. So I'm going to have a number that's bigger than 1 here. Yes, ma'am. Mm-hmm.
What if what we substitute in stays the same, and you get an answer that has the same in the problem?
What do you mean? Like if we substitute in here?
No, in the parentheses.
Here?
Yeah. What if we substitute, and let's just say we substitute in that number, and then we get in the problem they have that somewhere.
This like initial 2 million?
No.
Oh, okay. I'm sorry. I'm trying to follow.
So I'm saying, what if, let's just say I got that answer,
Mm-hmm.
right? And then in the problem they say, 1.04 is somewhere in that problem, and what would we do to the graph in the table?
So in this case, right here, what we're going to do is we're going to substitute in values for t. We can pop it into our calculators and figure out, like, okay, we know they started off with 2 million people. So how many people will there be next year? So that would be in year 1. Or we could substitute in, like, I don't just want to think about next year. I want to think about 10 years down the line. Then I could put a 10 in right here as I put it into my calculator. And we'll practice putting it into the calculator. Hello. Thank you, ma'am. Okay. Food supply. We said this was a linear function. Thank you. How do we write linear functions? Y equals mx plus b. So y equals, how would I write this?
The 4 million? 4 or 4?
4 million.
Plus.
So we're going to use 4, and that's going to go in which place? Is that my slope or my starting amount? Starting amount. So it goes in here. The rate that it's changing by, in this case, it's increasing, right?
4%.
0.5.
Wait, what? Oh.
Yep. 0.5 extra people. So that additional means that I know it's a positive. Their food supply isn't going down because they can feed more people each year.
What was it? I mean, like put 1.05?
This one would just be 0.5 times the time
4.
plus the 4 million people. All right. We want to know when they first experienced shortages. So what would I be looking for as I start to substitute in numbers and make a table?
Can you repeat that?
Yep, I want to know approximately what year will this country first experience shortages of food?
So like when the population's like higher than the food supply.
When the population is higher than the food supply. So we're looking for when this number is bigger than our linear function. I'm going to set you guys loose with this here in just a minute so that you guys can try to determine this. I'm going to show you how to put these things in the calculator. I'm going to use Desmos so that everybody can kind of see how I would type it in. These yellow calculators are going to be the exact same way. If you need me to tell you where some of the buttons are, I'm more than happy to, okay? So right now, they have a lot more food than they have people. In fact, they can feed everybody in their country twice over, right? So they probably have more than a year or two before they start to run out of food, right? Okay. So I'm going to go to Desmos. Are you guys okay if we say, like, what's it going to be in 10 years and use that as a jumping point?
Yeah.
Okay. So I'm going to go into Desmos, and I'm going to substitute 10 in the place of t for both of these. And what I would recommend is that you guys begin recording that and try some of your own guesses and checks after that. So I'm going to hop into Desmos. I love how my computer knows me so well. Okay. So what was our exponential function? It was 2 times 1.04
Well, T, but
to the power of t, and we said we're going to put in what as our first initial guess? 10 years. Okay, so I pushed this button right here for the power of. Yellow calculators, I can show you how to put in the exponents. 10 years. Their population is going to be about how big? 2.9 million, about 3 million people. Do they have enough food right now to feed that many people? So in 10 years, they're still good, right? Let's see what their food supply will be in 10 years. What was the equation for the food? 0.5. We're going to substitute in the 10 here. Plus 4. They're going to have enough food to feed how many people? 9 million people. So 10 years from now, they are still sitting pretty. They can feed everybody in their country 3 times over, right?
Wait, what's the? Oh, okay, yeah.
I want you guys to continue to iterate this. Continue to try some guesses and checks with different amounts for the year. Eventually, the population, because it's growing exponentially, eventually that food is going to run out. I want you guys to spend about, let's take about 5 minutes or so. Substitute in different values. You can use one of the yellow calculators. You can hop on Desmos if you want, but you want to substitute in different values in the place of time. Yep,
wait.
Okay, thank you.
you're welcome.
What did you get?
Yep.
0.5.
Yep.
This is kind of what they actually use to figure out, like, in America, if we ever have, like, a food shortage.
Yeah, stuff like this, yes. It's lots of moving parts, so it's more complicated, but it is based on these general principles, yes. When they look at, like, okay, we're okay, but, like, if these droughts come through and our ability to produce grain or to ranch different animals, if that goes down, how is that going to affect things? Or if our population is increasing rapidly. All right, take about 5 minutes. Use some guess and check here. head up for me, dear.
So, you want us to change the?
Change the value for T. I used 10. In 10 years, they're still fine, right?
So can I like put 20?
Yeah, try 20. See what happens. See if they're still okay. Yep. Guess and check with whatever numbers you would like. Since 10 years was more than okay, I'd probably jump farther into the future.
No, they're dead.
Kayla, go to 200.
200?
That's what I did.
Y'all are playing.
What did you find when you went to 200?
Hold on, I found that
Everybody hungry.
the population will be more than the food supply.
Population is definitely going to be more than the food supply at 200.
Yes, by a lot. It's like 104 million.
They can feed 104 million people, but they have how many?
5 million.
What's more than a million?
Million?
5 billion people. Okay, so 200 years out in the future, they're starving.
They're done for.
Okay. Can we narrow it down more than that?
Yeah.
Okay, what should I try?
1,100.
80? Okay, let's try 80.
Narrow it.
You said bigger? You said 500. You don't want them to eat at all.
No.
All right, what do we have here at 80?
44 million food?
They have enough to feed 44 million people, and their population is
46.
46 million people.
6 people? No.
There's 2 million people that are going to starve,
Yeah.
So
right?
This is like right where it starts. Though.
Can we narrow it down more than this?
It's 79.
Let's try 79.
75.
Let's see if they're good or not at 79.
No.
Still starving.
79, what do we have?
78.
Let's try 78, because we still have about 1 million people starving here.
Actually, 78 might
So
work.
78.
It's gonna be like 0.55.
Right. Oh.
Ooh, right about here. So 78 years into the future, they're fine. But 79, that's when they start having problems. So do they have time to plan?
No.
Yeah.
Oh, yeah, yes, they did. Yes, they did.
Yeah.
Yes, they did.
No.
They know.
We're out here at about 78 years. So
I can't.
about 78 to 79 years.
That's when they're good. That's when like they're still good. They have when they
78, they're good. 79, they have shortages. So I would say like 79 years probably. So they have almost 80 years to plan. All right, so did you guys get a feel for how this was when you were playing around in Desmos?
Yes.
And how to find some good numbers to use for the guess and check?
Yes.
All right, I want to use this idea now to look at part B. Look down at the question in part B. So the country doubles its initial food supply, but they don't change how much they're growing each year. They just add more stockpiles right now. Did it tell us anything about the population?
No.
Wait,
Oh.
additional
4 million people. No. Wait a minute. Ooh.
Did anything change about the way the population is growing? No. So I would still describe this with what equation?
The what? The
Y equals
that.
Yep, the exponential one. So the population equation stays the same. They're still growing the same. So what about the food supply?
It's change. It's shortage. I mean, no.
What are they saying they're going to do? Double the initial food supply.
Yeah. Because they knew some people were.
So it would be enough to feed 8 million people. But they're not doing anything to change the incoming supply. This is the rate that they described. So my rate stays the same, just the initial amount changes. So what would this equation look like?
Y equals, yeah,
Mx plus b, so what are we using for m?
the starting point. I mean,
0.5
Oh,
plus 8.
where'd you get
So I want to know the
Never mind.
rate stays the same, the initial amount doubles. When are shortages going to occur?
I don't know.
So I want you to answer the same question here, but now they're starting off with more food in storage. See how much time that buys them. 79 years before is when people started starving. How much does it change if we double the initial amount? Mm-hmm.
Do we substitute anything for the differential equation?
You're going to substitute in a value for t, just like we were doing. Let me fix this here. There we go. We already know that the old number, when this was a 4 back here, that we could get to about 79 years, right?
Yeah.
So about 81 to 82.
You got 81 to 82? Let's sub it in and see.
Wait, isn't that a 82? It's like 2.
All right, so this number is now an 8. Yeah, they're good to feed people here at 78 years, right?
Half a sandwich.
Are they still good at 80 years?
No.
Are they not?
Are they still good at 80 years?
No, but
Here's their food.
Yeah.
they have enough food, but not enough.
Yeah, the
That's okay.
Yes, myself.
Oh.
Having more food than people, everybody gets food, right?
Yeah.
So if they double that initial amount, they're good at 80 years, right?
Wait.
What about 85 years?
No. That's what I thought. No.
At 85 years,
They don't have enough food.
they don't have enough food. How many people are starving?
6 million.
6 million people are starving.
That's crazy.
Okay, so 85 years is too much. What about 82 years?
They don't have enough food.
Let's find out. Do they have enough food?
Yeah. Well, no.
Not quite. They have enough to feed 49 million people.
So would you round that like to 50? No.
Yeah, they have about 50 million people, but they don't have enough food for 50 million people.
One person's gonna die. Is it
So what about 81 years? Do you think they'd be okay at 81 years?
Maybe a cusp, probably. Yeah.
Yeah.
Yes. They're like right there.
I guess if they had like 4
They're done for.
So between 81 to 82 years in the future. 82 years is when they start to experience those shortages, right? So how much time did they buy themselves by doubling their initial food supply? Yeah, just like 2 to 3 years.
They tried.
They tried. They bought themselves a little bit of time. Was it super effective?
they use their time wisely.
If they use their time wisely, yes. Look down at part C. What are they describing changing in part C?
They doubled the rate of food supply.
They double the rate in addition to doubling the initial food supply. Are they telling us anything different about the population? No. So population, I still have what equation?
Oh, the two times 1.04.
Yes. Y equals 2 times 1.04 to the power of t. Let's talk about this food supply equation, though, because this is what they're describing as being different. I know it needs to be y equals mx plus b.
So they doubled, since they doubled it.
They doubled the rate. What was the original rate?
4? Well, 8?
What was the original rate?
Oh, yeah.
0.5. Double means to multiply it by 2. They used to have enough, like they were producing food fast enough to feed an additional 500,000 people a year. If they double that rate, they'd be able to feed how many extra people each year?
What?
An extra 1 million. So I'm going to have 1t plus, they've doubled their original food supply. What was their original food supply?
8. I mean,
It's adequate for
4 million.
4 million, and we're doubling that. So 2 times 4, we have enough for 8 million people.
Oh, 8 again.
Yep, 8 again. They're not doubling the initial supply again. We're just making one change each time.
Okay.
Will they still experience shortages?
Probably in 90.
We'll find out. I want you to investigate and find out for me. Will they still experience food shortages? And if so, when will that happen? Are they still going to experience shortages, and if so, when?
Oh, 90 years ago.
You have a book for this class, right? You have a book for this class, right?
Yeah, that's that one.
Oh, okay. I just wanted to make sure that you did have one.
They will.
At 500 years.
At 500 years, they're going to be starving. Okay.
They got.
102 to 103 years. Let's look at it. So I need to change this right here to a 1. Oh, I shouldn't still have the 0 out in front. So they're good if they double the rate at which they're producing food. I heard to try 100. Are they good at 100 years? Yep. Food is bigger than people. We're good. 500, yeah, they're probably starving there.
I'm starving right now.
101 years, are they still okay?
Yeah.
Because it went up.
100.
Let's try 102. Are they still okay at 102?
Yes.
What are you noticing though?
It's
It's getting kind of tight.
I mean, it's the closest.
I did 105.
You did 105?
Yeah.
Let's see
I think that's
They're done.
103.
It's she's doing 103 though.
Or it's 102.
Okay.
Yeah.
So
Yeah.
103.
So in between 102 and 103 is probably about when that's going to happen.
Yeah.
You got 100.
That's what I'm gonna do.
103 years. They're done.
Yep. So about 102 to 103 years.
No.
In 102 years, it's tight, but they can still get by. 103 years, people are starting to go hungry.
They're dead.
Hopefully not. Hopefully everybody eats just a little bit less. Everybody's fed, just not fed to full.
Some bugs, protein.
Okay. I want to spend our last couple minutes looking at one of the problems that's from the homework that is assigned for today. So we'll look at one of these together so that you have some idea of what I'm asking for on some of these questions. In your book, this is on page 116. It's part A up at the top of page 116. If I'm looking at this equation right here, is that linear or exponential?
Exponential.
Exponential.
I don't know why or how, but it seems right.
Exponential functions have an exponent on them that is a variable. It's an amount that can change. So if you see an exponent up here, and it's not just a fixed number, that's an exponential function. Where do I go looking in an exponential function for the initial quantity? Where's the initial amount?
In the parentheses?
Out.
Out in front of the parentheses. It is 8. This is the same thing as the y-intercept.
Oh, do you have to write
So
the
here's the initial amount. This is showing growth. How do I know? Inside the parentheses, what kind of number do we have here? Yep. Positive, and it's bigger than 1. If this is bigger than 1, that's the same thing as 1 is the same thing as 100%, then it shows growth.
I wish I had the questions on here.
So if I want to determine the growth rate, if 1 is the same as 100%, what is this as a percent?
You have to divide by 100 to see.
It'd be 123%.
I thought so. I don't know why.
If I want to figure out how much it's growing by, I'm going to subtract 100% off of that.
It's gonna be
23% is the growth rate. If it was decay, I would have a number that's smaller than 1 in here, something smaller than 100%. I would still subtract 100 from it. I'm going to end up with a negative here. I would just write the percent part, not the negative. The negative just tells me that it's getting smaller or it's decaying. I kind of gave away the third bullet point, but I gave that away with the second one. How did we know it was growth?
the number was it's bigger than 100.
Yes. The base, b, that's the number inside parentheses, is bigger than 1. How could I make a rough sketch of this? What do you think it would look like on a graph? What did our graphs yesterday look like?
It's like curved.
It was kind of curved, right? So if it's growing, would I expect it to curve upwards or curve downwards? It's going to curve upwards. So I'm going to have something like this. Where does it start?
At 23. No.
What's the initial amount, the y-intercept? 8. So it's going to go through the 8, and it's going to curve upwards. Remember, it's never going to drop down below the x-axis. There's no way it could become negative. Let's try to come up with a story that would work with this. Think of that context that we were just reading. We want some kind of a story that goes along with that. What kind of a situation would start with 8 of something? Maybe it's 8 million, maybe it's 8,000, and it's growing at 23%.
8 red pandas.
8 red pandas, okay.
Okay.
Sounds good.
Okay.
There are 8 red pandas initially. I have to say something that tells me that that's at the beginning, right? So whether you use the word initially or not, there has to be something that tells me that's the starting amount. There are 8 red pandas initially, and what?
123.
their population is growing or decaying? Is growing. Growing by what? What did we say the percent growth was? Yes, their population is growing by 23% each what?
Each year.
Each year, that sounds good. You have to have some way to measure t or time here. So in my story down here, I needed to explain the initial amount. I needed to say whether it was getting bigger or smaller, so growing or decay. I needed to say by how much, and I needed to pick a unit of time. Your homework assignment is asking you about are things that are being described linear or exponential, and then it has several things like this where I ask for the initial amount. I want to know whether it's growth or decay. I want to know what the percent growth or percent decay is. And for, I think, 2 of them, I ask you to sketch a graph and write a story. All right? Have a fantastic rest of your day, guys. I will see you tomorrow.